So, hello, dear colleagues. I welcome you to the 223rd meeting of the seminar of Moscow ACM SIGMOD section. And our guest now is Pavel Velikhov from TigerGraph. And his talk will be devoted to massively parallel graph databases. So, Pavel, the floor is yours. Welcome.
Okay, thank you. Welcome, everybody. My talk today is about massively parallel graph databases, and I believe that this is going to be the future of data analytics. And in this talk, I will try to explain why I think this way, and maybe we'll have a good discussion if you want to challenge this this crazy idea. I am currently Director of Engineering at TigerGraph. You see two logos on my screen. One is TigerGraph, another is Nebula. These are the two MPP Graph DBMS systems that I'm going to talk about today, mostly about TigerGraph because I'm mostly familiar with TigerGraph, but also a little bit about Nebula. And I'll explain why. There are actually, as you probably know, there are tons of different graph database systems out there right now, but the ones that really can challenge massively parallel relational technology, there are very few, in my opinion. So the main points of the talk are going to be the following. We'll do a quick introduction into graph databases. Then I'll show you how TigerGraph and Nebula beat relational databases at their own game in all app settings, and also present some additional analytic capabilities that graph databases have over relational, and then some extra things. So these are already pretty big things. We can go pretty far with just the first two bullets, but also a new thing that comes with graph databases is an ability to run parallel graph algorithms on big data in a very convenient way, which hasn't really been done before. And finally, also a nice thing that graph databases allows is in database machine learning, which has been tried before quite a lot in different systems, but I believe finally in graph databases this will be successful. Also, we can discuss this if you don't think that's the case. Well, there are lots of graph databases. Here's a list from DB engines. This is, I guess this is, the rank here is how many Google searches were on this database. And there are more than 30 databases here, and TigerGraph is actually number 9 on the list, and Nebula is number 15. So why don't we talk about others? Well, all the multimodal databases, I'm not going to really talk about them at all because they haven't built in a powerful graph query language into the database, so it cannot really handle complex graph queries. And other systems, they either don't provide massively parallel capabilities, or performance-wise they're really bad, or they don't have a powerful expressive query language. Just a little more detail. So for example, Neo4j is really popular graph database systems, but it has no capability in MPP at all. So it's a single node machine. You can install multiple instances of Neo4j and somehow mediate over them, but it doesn't have real MPP capability. And also, we want a powerful query language that will lead us to GQL, upcoming standard. I'm going to talk about it. So we have some systems like Janus Graph and dgraph that are massively parallel, but they have a really basic query language that doesn't allow powerful querying. So it's not very interesting. And finally, also, there are a lot of startups right now in the area, but we're looking at kind of enterprise-ready solutions, so mature products. Here's a quick introduction into graph data. Everybody here, I'm sure, knows what a graph is. So you have vertices, you have edges between vertices. You can attach attributes to vertices and attributes to edges, and then you can query this, right? So, but one important thing about graph data, about graph databases, we can split all the databases into two sections, into two buckets. Ones that require a rigid schema over data, and one that allow kind of a NoSQL kind of approach to data, where you don't specify what attributes you have on the vertices, and you don't specify what attributes you have on the edges and their data types. So in TigerGraph, we have rigid schema, very similar to relational schema. Every node, every vertex, and every edge must have a specified list of attributes with a primary ID, and the data types must be specified as well. And I think this is a really important distinction here, because first of all, with all my experience in NoSQL, it's a nice concept where you don't have a schema to start with. You start building an application without worrying what data you will store. But then at some point, when you start building algorithms, when you start analyzing the data, you end up requiring a schema anyways. The benefits are just to get you started, and then they turn into liabilities. And with a graph schema, you get a lot of performance improvement. So you get great compression in storage. You have good query optimization opportunities because of type inference, etc. So it's really a big boost. And so finally, so where do what data do graph databases work on? And so usually when you talk about graph databases, you say, okay, it must be some social network analysis or some big transaction chains or something like that, right? But in reality, all relational data is actually graph data in a way, right? So here I have a typical entity relational diagram that we all use to design our relational databases. And we have a vertex shopper, we have a vertex item, we have an edge bias in between. So it's a natural graph representation. So every entity will be a vertex, and every relationship will be an edge between vertices, right? Well, assuming we have only binary relationships. So actually, what we do in relational databases, and especially in OLAP, we take this big data set, which is a graph data set originally, and we break it into tables. So vertices get a table, edges get a separate table. And then typically in OLAP scenarios or star or snowflake schema, we reconstruct for each query, we reconstruct all the not all of them, but some of the relationships back into one big table, right, to run aggregations. And this is really expensive because we're using joins. We're using like hash joins or merge joins, and they're pretty expensive. And we can handle at most like 10 to 15 joins in big data systems, right? So maybe a little more, but not much more. And there's been tons of work in join order optimization and join algorithm optimization, and it hasn't paid off that much. So what's wrong with joins? So we have a simple simple schema here. So a person buys a product which is produced by a company, And no matter how you, although this is a simple graph, and you would think that maybe there's a strategy that would, in one pass, give you the result without having to do expensive join operations. It's not really the case. It's not easy to fix it. So I claim that here, no join strategy will really efficiently solve the problem. We'll still have to do a hash join or merge join somewhere, and it will slow things down. How do we do this in graph databases? So in graph databases, we fix this problem with storage in the following way. For each edge, we store both directions. So for example, we have a bot edge that goes from person to product, and we would have a bot by edge that goes from product to person. And also, so we have a producers table storage segment and produced by storage segment, right? And inside they're clustered on the incoming edge ID. So basically, to do a join here in the graph database, for example, we start with person one. We go to the bot storage. We have a clustered index there, so we scan contiguous amounts of memory very quickly, and then for each product we can look up its name in another table, in the product table, and for each produced by edge, we also go to a clustered storage, and we get the company name. So this strategy allows us to do to beat relational databases on all up scenarios with we can do maybe now 20-30 joins, so almost like twice as many joins as relational systems can do. And this is really this was a eye-opener for me when I joined and started figuring this out, because I think it's a very big deal, because right now we have a lot of linked data. We want to analyze all these relationships, and 30 joins becomes a pretty common query. So you can say, but it's not just joins in OLAP. We have subqueries, and we could have a subquery with a group by an aggregate. So how could we? So suppose that we take this strategy and apply it to relational systems as well, but we'll have subqueries and group bys and aggregates, and it's quite common, right? And graph databases, specifically TigerGraph, we have a separation between edge processing and vertex processing and aggregation. So here's a quick crash course into our query language. This is GSQL. And here's a query that is trying to go from customer to product and compute the sales revenue and for each customer. So how much each customer bought. So what are the revenues per customer? What are the revenues per product? And so here we declare two accumulators that are kind of separate from query processing. And then we run a query. So the query looks a lot like SQL. We select some node, some vertex C. From is a typical kind of, you can look at it as a SQL from clause, where you have a relation customer edge, or vertex customer goes to edge bot and goes to a product. And we compute the revenue with the attributes of the customer, bot, and product. And we increment, so we increment our accumulators. So we add things to the accumulators and compute the aggregation this way. So this allows us to to separate aggregation from querying. So we can have a complex pattern in a query and aggregate it kind of on the side. So we don't have to kind of mix it with subqueries or anything like that. And another concern you may have is, what about n-way relations? Can we handle n-way relations? Well, it doesn't seem to be that common in business analytics, and I think it's also possible to break them up into binary relations. It won't be that, it won't look that nice maybe, but it's quite doable. So, so that was the first thing about why graph databases, well, specifically massively parallel and high performant graph databases can be the future, because so far, even on OLAP, on these join queries, we beat existing relational systems. But also we have the ability to consider variable length paths in our queries, which is of course in some way doable in SQL. You have a recursion capability in SQL, but it's typically not used in MPP systems, and it's very few people actually use it. It's very cumbersome. But in graph databases, we can process and analyze such paths. And finally, also an important thing is that the output of a query in TigerGraph can be a graph. So usually relational database, the output is always a table, and you can look at the table, you can display the table, you can aggregate it, and have maybe in OLAP systems, you have drill down and pivots and nice things like that. But sometimes you need to look at the graph actually. So here's an example from a fraud detection use case. We have an algorithm that identifies potential fraud, but then an analyst has to come in and actually look at the actual data at the graph and see what is this node connected to, and what are the, how does it look visually in a graph? Is it really a fraudulent user or not, right? And so again, this is a nice capability of graph databases, that you can quickly grab a piece of a graph and display it, and have the kind of mix querying and navigation in the graph. So the question is, why not switch right now to graph databases? And well, our plan is to do exactly that. We want to kind of go against the big OLAP players in the industry. But there are some challenges that remain, of course. So the technology is still kind of young, and we can't scale to petabytes yet. So we're working on it, but it might take a couple more years. And all analysts has also, you know, they've learned SQL, they're using SQL. It's very hard to make them learn another query language. Right now, currently, there's no standard for graph query languages. There's an upcoming standard. I'll talk a bit about it a little later. But we're not done yet. We have extra capabilities that graph databases bring, and I think one of the most exciting ones is graph algorithms on big data. But even other things are so for machine learning, things are pretty nice, I think. So we enable much more complex features for machine learning using graph features that we extract with all these joins. And we support graphlets and embeddings from the graph data, which is very useful for quick and dirty machine learning systems. So everybody who wants to do some AutoML or some simple model can grab an embedding of the graph, like a node to vec embedding, and try a classifier immediately and see what the results are. And finally, there's some benefit. I think we're trying to push this area right now in database machine learning, and there are some really strong arguments why it should, why it's really important and why it can fly. So first, graph algorithms on big data hasn't been done before. And of course, you know that PageRank was built on MapReduce a long time ago. There's some algorithms in GraphX library that are also MPP. But these are separate systems, so it's not, you don't operate on the data in your database. You have to export the data, run it on some other cluster, get some results. And for example, even in GraphX, there are not that many built-in algorithms there. So I just checked recently, and I haven't found many. So there's a framework, you can build your own, but it's not like a nicely nicely built library that you can just use. And there's technically a MADlib package for Postgres-based databases like Greenplum, which is an MPP database. But actually, the graph algorithms in MADlib are not MPP and are pretty limited as well. So I think that maybe TigerGraph is one of the first systems to unlock MPP graph algorithms on big data. And the use cases for this are, there are a lot of use cases, of course, because, you know, when you're doing fraud detection, you want to look at communities that are closely tied together. And if there's a lot of fraud in the community, you can just ban the whole community, for example, or also some like complex scenarios where you're trying to find money laundering schemes or things like that. Graph algorithms are really, really useful in these cases. Also in recommendations, you want to compute similarities between nodes in a graph and use graph features as or graph connections around your nodes for similarity. Also, it's a graph algorithm. And so, and the final thing I want to talk about is in database machine learning, and kind of well, this is a bit. So we haven't reached success in this area yet, but I believe that this will be really important. So if you have any objections, please stop me and say, well, if you object. So how do we usually work with machine learning in a database? And the usual scenarios, we download a sample of data in our Python notebook into memory. We extract some features, we build a model, and then we deploy a model into a separate service. And we have to build a separate data pipeline for this service, which is really which I believe is a really problematic thing, right? Because imagine a big enterprise database, graph database, or OLAP database. You have a huge set of ETL tools, data cleaning tools, all bringing data, integrating data, and bringing data into the database. You build a model on top of this data. Now you want to build a real-time scoring service. You need the same data in real time. So you have to kind of replicate the data pipeline for your service. It's a huge problem, and a lot of people still do it. And actually, here's an illustration from a seminal paper about technical debt in machine learning systems. So the actual machine learning work that you do is usually really small, actually, compared to data collection, feature extraction, and analysis tools, and serving infrastructure, and monitoring, and all these other things, which you already have to have for a database. So why do you have to replicate them for machine learning? So in database, we can solve this. We can, of course, also download a sample from a graph database to start with, or we can train a model within a graph database. But this is kind of usually, data scientists prefer their Python tools, so it's okay. We don't have to force that. But deploying a model within a graph database has a lot of benefits. So you don't need to replicate the data pipeline, or you don't need to build a separate service. The database is already a service. And you have a lot of options to perform real-time scoring. So you can do it query-based, so run a query that will score new incoming data, or put a trigger in the database and have the trigger score every incoming vertex, incoming edge, etc. So I think this will be a big boost to machine learning guys when they're scaling to big data sets and real-time scoring. So I think I'm ready to conclude now. So I think I've kind of shown a little bit that we can beat relational databases on their own turf, which might not last that long, because probably they'll figure out that graph databases have moved quite further than relational databases, and we'll come up with a way to fix it. Maybe add a graph language to relational systems and rework the storage and kind of go there. So there's, for example, a standard coming out from ISO this year. It's an SQL extension for graph queries, right? So this might solve some of the problems. But we also have new analytical capabilities, this variable length path. We allow parallel graph algorithms on big data, which is a big thing, I believe. And as maybe a small thing right now, but who knows, maybe it will become important, is a better way to train and deploy models for graph data. And just kind of peeking into the future of MPP graph databases. So these systems, TigerGraph and Nebula, they're really young. They're just a few years in the industry. Right now, everybody has their own query language, which is a problem. But the GQL standard by ISO build SQL standard, and they don't build many. They only pick standards that they really believe in, and so they pick GQL. So they really believe in graph technology. So that standard is coming in 2023. Right now, TigerGraph doesn't scale to petabytes yet, but I believe that in a couple of years we will. And of course, we have a Russian audience mostly here, and the TigerGraph is closed source proprietary system, so you can't safely use it in countries like Russia, but there's an open source alternative out there, Nebula. It's a little less mature, but it's going the right way, I believe. So it's maybe it's a good time to get on board, and I've compiled some useful links to look at. So just websites of the systems. We have a small demo of interactive analytics if you want to look at that, how it's done with graphs. Also, we have free versions of the system to play with. They're limited, but they're pretty nice limitations that allow you to play with big data. And finally, we run our own conference. It's called Graph and AI Summit. And there you can look at different scenarios, how our customers use the product and what they're doing. And it's pretty technical. We also have some really interesting things that I didn't touch upon, is hardware accelerated graph algorithms that we do there, but haven't gotten into that. So this is the conclusion. Thank you. Does anybody have questions? I would love to have a discussion.
Okay, Pavel, thank you a lot. But I have to say, so your talk was quite compact comparing with the regular talk on the seminar.
Oh,
so
okay.
so we have quite a lot of time for questions and discussions. So everybody, you're welcome to ask Pavel on some details of graph databases, maybe especially TigerGraph or Nebula or so on. So please, do we have some questions right now?
I have one question. Can I ask?
Yeah, sure. Yeah, sure.
Have you checked Grail? So there's a system, it's basically research-based system from the Madison guys. So they develop so high-level DSL for graph, and they have some system which is open source as well. They convert this high-level graph query into a set of SQL queries and execute in a database. And they have a paper. They also talk about some optimizations there, that how they do. So
there's a lot of things in the literature. I haven't looked at this one. I'm a bit concerned that that they actually translate a graph query into SQL, which seems, yeah, I think you can lose a lot of advantages of graph databases if you do that.
Yeah, just asking for curiosity.
But no, I haven't looked at that. Well, you know, right now we're in the startup mode, so we'll look at papers, but only the kind of the most seminal ones. We don't review too much literature at this point in time.
Okay, thanks.
Thank you.
Okay, thanks a lot. So do we have more questions to Pavel?
Yeah, one question.
Yeah, sure, Roman.
Yeah.
So who was the first?
Okay.
Okay.
Short question from my side. So
okay.
What you can say about application use cases, best use cases of the TigerGraph? Because I see, for example, for Virtuoso, one, maybe the best case was DBP deployment.
Okay, yeah, TigerGraph, the early use cases were that really helped spread TigerGraph around the world were fraud detection and anti-money laundering. So fraud detection in different areas in telecoms, in payment systems, etc., and anti-money laundering in banks. So there you have to look at long chains of events, long chains of transactions from one entity to another, and collect a lot of features along the way, train machine learning algorithms, and predict who is a fraud and who is laundering money. So those were the two big things that propelled us forward. Now we're doing a lot of other things, like we have a really great case in supply chain management. So also it's a long chain for network companies where you have a huge supply chain. You need to analyze it quickly. We're doing a lot of stuff with recommendations also, because it's very linked, highly linked data.
Okay, thank you.
Thanks a lot. So do we have more questions?
Yeah, sure. Actually, I have a lot.
Oh, good.
First, theoretician proved several years ago that if your query language is based on Boolean logic, you inevitably should have relational calculus inside that, or if you add recursion, you have an equivalent of data log or something like that. So and when I didn't look much at different graph query languages, but everywhere where I tried to find out something, after some preliminary like data filtering, extraction, or whatever, the language ends up with sets of vertices or or edges, whatever, and then there are the sets, and then you cannot do anything else except joins or whatever is in we do normally in relation. So my question is, my first question is, you mentioned long chains, which means in terms of more abstract concepts, means recursion.
Not necessarily, but yes, recursion or just a lot of joins, yes.
So what you do, you have some better way to do joins because you have pre-stored links like in edges. So you can do joins better than regular algorithms, or you have something else.
No, it's yes. So the way we do joins better is because of storage organization. So because yes, we have clustered. So for edges, we store them in a clustered way where they're clustered on incoming vertex, and this way we can easily kind of in one pass go through the data and kind of sort of avoid the join in a way. So it's or do kind of yeah, I'm not sure what the relational equivalent of this would be, but like I think it's
sorry, you cannot avoid join. You can do it differently, probably.
Yeah, yes,
because
yes,
you have stored links.
Yes.
But theoreticians say that when you do things like that, you actually do the joins.
Yeah, yes.
So you cannot avoid them.
It's a join, but it's more efficient in a way that it's like I think it's even more efficient than merge join, right? So it's kind of like, yeah, if you prepare your data correctly, then you have the ability to do these joins really fast. The thing is, relational systems are optimized to do any sort of join, value-based join between any kind of entity, right? But in practice, it turns out that we end up doing joins mostly between foreign and primary keys in the database anyways. So between the relationships that already exist, and we're restoring them. So here the philosophy is we keep these edges stored in a better way to do better joins. Yes.
Okay, probably not many people remember that similar storage structures were used in IMS 360 and 370, like decades ago. And that actually that system was really fast. Nobody could beat it in the performance. And this will never be, because they had reasonable speed at the computers of that time. Anyway, they also have some other nice ideas. The only problem was the absence of like query languages, and it was really hard to learn how to use it. But technically you are doing similar things. You, in certain sense, you pre-calculate joins and store them. So
yes,
based on that, then you say massively parallel, but do you distinguish massively parallel with shared memory and shared nothing systems?
well, so it's kind of murky right now. It's becoming a little murky because, again, we're a hybrid system. We work on premises and in cloud. And in cloud, we utilize the shared storage, like Snowflake does, for example. And we keep caches on local disks, and we can pop up multiple clusters. So it's kind of it's mostly shared nothing, but it has an element of shared disk, which is
Okay.
cloud storage. Yes.
Okay, so actually you are not looking at machines with like multiple CPUs with like hundreds cores in total.
Not really. So we're looking more at the machines that are available in the cloud, which are, well, we have these machines are also have good internal parallelism, right? So we leverage that. So we leverage multi-core as well. So we will, but we're scaling. We're scaling because we can scale to hundreds of machines, not just a single machine.
Yeah, but then you have to do communications. Anyway,
yes, of course.
Anyway,
Yeah.
I got the answer. Then, okay, probably final comment is in one really old book, there was an excellent statement. Any hypothetical software has very powerful capabilities. And what you was talking about is more significantly in the future.
Well, some things in the future. So we already do joins and we already do benchmarks pretty well. I haven't, the thing is, well, the benchmarks in graph databases are not, just came out, right? So the LDBC benchmark is a graph benchmark that just came out, and we don't have any numbers except TigerGraph on it yet.
Okay.
But yes, we're of course we're pushing for the industry to adopt benchmarks, but it's hard because the industry.
Yeah, sure.
Yes.
So it is. I think you might want to keep this in mind because, like, something of I agree that something of not everything, but something you mentioned is in the future. So it is really powerful just because it is in the future.
Yes, I agree. Especially, in database machine learning, that's something in the future.
Yeah. And you still you mentioned that data scientists do not want to move to any kind of databases. That's very true, and they cannot actually. There are some reasons why this happens. But probably you should look at data engineers instead.
Yes.
Okay, then thank you. That's it from me for now.
Okay, thanks a lot for nice questions and for answers. Do we have more questions for the rest of the auditory?
Yes, I also have a couple of questions.
Yeah, sure, you're welcome.
So my first question is, are machine learning tasks run on the nodes where data is located?
Well, right now we have yes, we do run So depending on what tasks you're talking about. So scoring we can run in parallel on every machine. So when you have a model that's done and you have data distributed between machines, it's very easy to score in parallel. Training is a problem because usually, for example, algorithms like gradient boosting algorithms, they don't parallelize well and they're sequential inherently. Or a neural network, to train a deep neural network in parallel is pretty hard. So we don't do it at this point. So usually right now we can score, right now we score data on the system, but we want you to build the model separately right now. So, but we're also building in capability to train inside the database, but it will probably be less parallel. So maybe you'll have to start up one machine with GPU, train the neural network there, and then for inference, you can use all of your machines to do the inference.
I got it. So you don't support at the time, for example, distributed training when nodes share, for example, gradients?
Right now, no, we don't do it.
Okay, and my second question is how does TigerGraph isolate resources for example, training and other queries? Because training can be CPU consumpting process and inference as well.
So our idea right now, we don't do a good job. Actually, we just, yeah, if you train something, it may slow down the other queries. Our philosophy is the following, though, that we want to go the Snowflake route, where if you want to train a new model, you start up another instance, another couple instances or one instance of TigerGraph that has access to the same database, and you do your training separately from the cluster that's working on other applications. So you can do it through the cloud, so without interfering with other clusters in the cloud.
Okay, I got it. Thank you.
Mm-hmm.
Thanks a lot. Do we have more questions? Okay, maybe I have a questions. Returning back to the benchmarks and comparing the performance of joins between TigerGraph and relational databases.
Mm-hmm.
Do you have some benchmark on comparing this stuff? Maybe yes, some.
There's a paper by our chief scientist Alan Deutsch. It's called Tag Join. They compare TPC-DS queries, but that's they actually show that on like half of TPC-DS queries, TigerGraph outperforms in-memory column store systems. So it's I will probably add it to the presentation when I send it to you, Sergey.
Oh yeah, thanks. Okay.
That'll be good. Yes, I forgot to add this link. The problem is though that TPC-DS on average there are maybe like 6 or 7 joins in the database. So there are not many benchmarks where you have more than 30 joins. There are none actually, except for LDBC, which is a graph database benchmark. And LDBC is a new one, and yeah, it's very hard to get numbers yet. We have numbers for TigerGraph, but we don't have numbers for other systems yet. So, well, on small scale we do, but large scale, the systems don't scale yet. So.
Okay, thanks a lot. So, do we have more questions? Okay.
One
yeah,
other question here. So,
yeah, welcome, please.
Is it possible to update data in real time? Because one of the issues of graph databases, again, like Virtuoso, is absence of ability to update data, especially when we're doing it in parallel transactions.
Well, TigerGraph is we're considering ourselves an HTAP database, so we do have, yes, it's possible to update. Now, real time is a question. What is real time really? It's possible to update, and we do have strict consistency guarantees. But if you have a huge stream of transactions against TigerGraph, yeah, it's not going to scale as well as OLTP databases, of course. So it's mostly an analytical database, but with some capabilities of transactional data. So if you don't have too much, if you don't have much conflicts in your transactions, then we'll be fine. But if there's a lot of interactions in the transactions, a big stream of transactions, it might slow down the database quite significantly.
Okay, I'm just trying to imagine what might be use case, but for example, let's see, something like data, for example, like LinkedIn data or social networks. So do you think that data might be processed with TigerGraph?
Oh, yes.
Including data update from user side.
Yeah, so things that so some queries that some analytical queries that are run in LinkedIn, they might be pretty hard to run because they're they require kind of separate system. For example, LinkedIn has their own PNOT system to do analytics over real-time analytics, right? Because for every user you can request to see, okay, how many different people from different countries viewed my page in the last 30 days and things like that. So those queries are a bit hard and they require separate systems. But things like detecting fraud or checking, running through the graph and seeing who can have more connections to each other, predicting connections, things like that. TigerGraph should be a good fit for that.
Okay, and one more question. How, for example, search by strings is processing? So what is known about indexes type? So what just trying to explain it. What might be happening, for example, if we need to do some fuzzy search or something like that one. And last year's actually very popular is embedding-based search, especially in big database.
We haven't done this thing. We can create embeddings. We create graph embeddings based on node to vec for machine learning, but we don't do search based on embeddings, or we don't have indexes based on embeddings. Yeah. Because
it's a very interesting question to find, for example, nodes around according to embedding, especially if it's a graph database.
So it could be similarity search in the space of embeddings. Well, we can do this.
Yeah, but see, actually, the difference in case of search in space of embeddings, we are doing it like some rough search. So it might be extremely inaccurate, but in database and graph database, you can recheck it by actual links between edges, vertices, I mean.
No, that's very interesting. No, we haven't done this, but this sounds very interesting. Yes.
Okay. Okay, thank you.
Okay, thank you. Do we have more questions? Boris Sinich, maybe you have some additional questions? No?
I can. Again, my question is somewhat, do you know any cases where graph structure might be like misleading? I know such cases, but do you consider these use cases?
I'm not sure. Can you explain a little bit? Because yes.
For example, people do some like hierarchical structures or graph structures to relate concepts.
Oh, okay. Mm-hmm.
Like this is less general, and this is a sub concept of another concept, and you have so. And then, if you try to go first up to the general concept, and then go again down to another branch, then you lose similarity very quickly. That is a problem. So people try to do that, and like recently, I actually it was a keynote of Gerhard Weikom at VODB 2021. He said that they used knowledge graphs for marketing purposes, but actually they consider it as a database because they use they need similarities, they need all that, they need semantics, but they prefer to find this somewhat differently, because just because the graph structure might be misleading.
So yes, this seems like so knowledge graphs and kind of ontologies and the semantic web and all the things that go together with it. It's kind of a different world from us. We don't really focus on these examples much. Maybe we'll, yes, we don't really, we usually work with very simple graph data that you have a device that created a transaction against this bank and something like that. So kind of.
Yeah, sure. You have different use cases, and you told that, and that was really important. But this, I would not say that this another world like knowledge graphs is not working. They do nice things and they work, but the graph structure is not really important in that case. They have some, but they can figure out some relations between concepts on top of that, I would say.
Yeah, we haven't done much with knowledge graphs yet, so maybe we'll
actually, my idea was that this may happen not only with knowledge graphs, probably somewhere else. So
any attempt to classify things into a graph structure by human thought, I guess.
Yeah, sure.
Yes.
Okay, thank you. So maybe I do have a couple of questions. So Pavel, according to the title of your talk, so you're considering these MPP graph databases as a future of BI, but we have to consider the traditional alternative, relational data warehouses. And as we know, traditional infrastructure of a data warehouse support, for instance, extensive construction of ETL processes. So are you going to extend the graph database infrastructure in this way?
So we're trying to make use of existing ETL tools as much as possible, because you know, some of the things they do fit our use case as well. Something we don't. So there's a big story in warehousing where you create a bunch of like chains and trees of views on top of each other, materialized views, or we don't really play in that game. So our scenarios are quite different. You usually just load the graph data as is, and then maybe you create some new edges for specific applications. So if you want to analyze some specific properties, you might need new edges to have the joins go fast. And then you might delete them when you're done with your analytical task. But we don't, so we have a slightly different approach to ETL. So we don't create a bunch of materialized views usually, but otherwise we're trying to leverage the tools that exist in the industry. So.
Okay, thank you.
Mm-hmm.
Okay, and maybe the last question from me. So let's try to look from the different way on the same problem. So concerning, I mean that the traditional way to deal with BI is to apply a multi-dimensional model.
Mm-hmm. Mm-hmm.
And what do you think about supporting this kind of view on graph databases? So is it promising? Is it required?
Well, a lot, yes. So people like multidimensional OLAP, right? We're trying to interface right now with the existing tools and support this kind of scenarios to some extent. I think, yes, it's important. We also see, as the data gets more and more linked, we see that these tools generate more and more joins when they talk to databases. So we see a good benefit of graph databases in this case, right? So I think in the future, maybe we'll be competing actually in the space with OLAP systems quite a bit. Something where we cannot compete is systems like ClickHouse, where you have a few tables and you do really fast aggregation over tables. So we don't go into that space, but we're in case when you do a lot of joins, that's where we want to play.
Okay, thanks a lot. So maybe do we have maybe some last questions, or actually I do not see any more questions, but I suppose that there were quite a lot of questions and answers. So Pavel, yeah. Thank you again for quite interesting talk and for answering also all the questions. And thanks for all the auditory. And okay.
Thank you, everybody. Yeah, I hope this was interesting for you and maybe useful even. So, yes.
So thank you all, guys. Bye. So bye.
Bye.